Okay. So, welcome everyone. Firstly, apologies for the small delay that is there. Yeah, day one hiccup. So, I'll make sure that it will not be repeated from tomorrow onwards. Okay. So, welcome to Home Institute and welcome to the GATE Champion Series for GATE 2025. So, we are starting with digital electronics subject. And, first of all, we'll go for the syllabus classification, subject classification. We look at the important topics we have in this particular subject. Okay. So like I've told in the previous session, we are dividing the syllabus on the basis of two factors. How difficult the topic is. Okay. So when you go vertically upwards, yeah, here you find easy to moderate topics, and here you find moderate to tough topics. Okay. Same way on the horizontal side, we are classifying on the basis of the frequency of the questions being asked. On the left side you are having a kind of low frequency questions, not so repeated kind of questions, and on the right side you have usually high frequency questions being mentioned. Okay. Yeah. So here, first in this revision series that we conduct in the next week or so, so we will cover this portion. Okay, topics which are kind of quite easy as well as which are repeatedly asked. So likewise, we are having overall 6 topics here, even though I have shown 7, but rather this is 6 topics. One is base conversion of numbers in number system, and one more is sign numbers. Okay, and after that, the next topic is K-map minimization, one of the most important topics. Yeah, now I hope it's okay. Can you just confirm if the audio is clear? Please confirm if the audio is clear. Is audio clear or audio issue is still there? Audio is not clear, please repeat if audio is not clear. Audio is not clear, please repeat. So guys, just repeat. Please tell me if the audio is clear now. Is the audio clear now? Yeah, trying for that only. Okay, so audio is clear. So now audio is used. Go on. Let me adjust the brightness also. Yeah. Yeah, I think the brightness issue is resolved right now. It's clear. Yeah. Okay. So let me restart day one hiccup. So please apologize for that. Okay, I'm apologizing for that. It will not be repeated from tomorrow onwards. Okay. Yeah. So like I've told, welcome to OM Institute and welcome to Digital Electronics subject. So in this series we will cover the most important topics for all subjects of GATE 2025, starting with the first subject, digital electronics. And like I've told in the yesterday session, so here we are classifying the syllabus into four parts, depending on the frequency of the questions that are asked in the exam, particularly GATE exam, and second, on the basis of how difficult a topic is. So on the basis of these two factors, we have divided the syllabus into four parts, and this is a wise way of dividing the syllabus and picking up the most important topics first, gaining the confidence, gaining marks and gaining the confidence, and slowly going into the other topics. Okay. So on the left side, on the horizontal side, if you see, you have frequency of questions being asked. So on the left side, you have not so frequent questions, not the questions, the topics which are not frequently asked being mentioned, and on the right side you have the high frequency topics being mentioned. Okay, and on the vertical side, easy questions on the bottom side, tough questions on the top side. Basically, easy to moderate and moderate to tough. Okay, and again, these can vary from person to person, student to student. Okay, so this is a list that I prepared on the basis of, in general, on the basis of an average student. Okay, so and in this series, first I will be covering these topics which are very frequently asked, first of all, as well as also kind of quite easy to learn, quite easy to understand also. Okay, yeah, the six topics that we will discuss in this series are: the first is base conversion of numbers in number system, as well as also next sign numbers. And once that is done, we'll go for one of the most important topics of digital electronics, which is K-map minimization, basically minimization of Boolean functions. And generally, we have many methods of minimization, but the very commonly used method and the easiest method, graphical method to use is always K-map minimization. And hence, in general, the topic is minimization of Boolean functions, but we generally go for minimization by using the K-map method. Okay. Yeah. So next topic is logic gates. Ultimately, whenever you minimize the Boolean function, what we use is nothing but we use logic gates to implement that particular Boolean function. So we discuss logic gates. We get a lot of questions on logic gates. In fact, universal logic gates in general, basic logic gates, etc. And then we go for another important topic, multiplexer. Okay, and multiplexer comes under the chapter of combinational circuits. In combinational, one of the most important topic is multiplexer. Not just from exam point of view, whenever you design circuits, okay, a typical digital circuit, maybe your mobile phone, your laptop, if you see the internal circuitry, one of the most commonly used circuit is nothing but multiplexer. Okay, and after that, counters. So here we discuss mainly the synchronous counters, which are frequently asked in exams. So here in counters again, we mainly focus on analysis first. Design also is there. Design is slightly tougher as compared to analysis. Always, any design-based problems or synthesis-based problems are slightly tougher as compared to that of analysis-based problems. So hence we'll discuss it, in a different heading as such. Okay. But yeah, here we'll mainly focus on analysis of mainly synchronous counters. And lastly, we'll discuss ADC and DAC. Okay, so these are the six topics we will discuss in the first flow of the session. Okay, yeah. So starting with number systems, we'll first start with number systems. Yeah. So when it comes to number systems, first of all, we have to know about the base conversion of numbers. So let me discuss some brief points regarding number systems base conversion, starting with base or radix. A brief review. Okay. Base or radix corresponds to the maximum number of symbols we are having in a number system. Okay. So this simply corresponds to the maximum number of symbols we are having in the number system. Okay. And after that, one very important point regarding base or radix is nothing but any symbol value that you take, any symbol value is always less than the base value. Okay. Or base value is larger than any symbol value. Okay. Okay. So this is one very important point. We will use it very extensively in problem solving. Base value is always larger than the any symbol value that we have in the number system. Okay. Next. Whenever we have a number, let's assume a number called as dn-1, dn-2, and so on, d2, d1, d0. And then fractional part d-1, d-2, and so on, d-m. And if I want to find out the value of this, finding out value is very important in number system. So if I want to find out the value of this is simply so this is a formula we use for finding out the value of any number. Okay. So basically numbers are multiplied with, this is a digit, this is another digit, this is the corresponding digits. And these corresponding digits are multiplied with the corresponding weights. So the weight for the leftmost digit is nothing but b power n-1. And the weight for the next digit is nothing but base power n-2 and so on. The digit that we have just before the radix point corresponds to a weight of b power 0 and so on. Next, fractional parts will have weights of values less than 1. So this is having a weight of b power -1. This is having a weight of b power -m and so on. Okay. So this is how you find out the value of any number. And value of any number is always obtained in terms of decimal format. Okay. Because we humans always tend to do the calculations, in decimal number system. So here we are performing some calculation, multiplication, addition, etc. So always the result is obtained in terms of decimal format. So this number is obtained in terms of always base 10. Always in terms of base 10, which is decimal. Okay. So this is one logic that we will use in order to convert the numbers from one base to another base. Okay. Let us see that. Yeah. So we are discussing here two types of base conversions. So two types of base conversions. The first type of base conversion is nothing but n base 1. So the number is given in terms of base 1. We ultimately want to convert this number into base b2. So what do? So we always go via decimal number system here. Okay. So the procedure here is nothing but convert that number into base 10. Just now we have seen how to convert that number into base 10 format by simply finding out the value of the number. Okay. By using the previous formula, find out value. Whenever you find out the value, you always get the answer in terms of decimal format. And once you get the number in terms of decimal format, from decimal format to base B2, the procedure is nothing but repeated division process. Use repeated division process. So we are repeatedly dividing that number with respect to what base? By using the base B2. So by the base B2. Okay. And then we get the answer in terms of base B2 format. We have another variant of this particular base conversion. The next variant of this base conversion is again another base conversion. So we have number given in terms of base B1 and we want to convert that number into base B2. But here both base B1 and base B2 are powers of 2. Okay. So here base B1 is basically a power of 2, 2 power n1, let's assume. Base B2 is also power of 2. Okay. So in this case, both bases are powers of 2. Both bases basically are powers of 2. So whenever both bases are powers of 2, so in this case, we don't go via decimal, we go via binary. Okay. So in this case, we convert that number first of all into base B2. How do you do that? By converting every symbol in terms of n1 bit binary format. Okay. So by writing each symbol in terms of n1. Okay, because base B1 is 2 power n1. So n1 bit format, n1 bit binary format. So in this case, no calculation, directly converting that symbol into binary format. And after that, we group the bits. We group the bits into groups of n2 bits each because we want to convert that number into base B2. Base B2 is 2 power n2 and hence here group the bits into groups of n2 bits each. Okay, so we are grouping the bits into groups of n2 bits each. And again, always the grouping starts from where? The grouping starts here from the radix point. Whenever you have a radix point, that is where the grouping starts from here. Okay, so this is regarding the base conversion of numbers when both bases are powers of 2. Here this logic you can use only when both bases are powers of 2. When only one base is a power of 2, the other base is not a power of 2, you can't use this logic. Okay, so here you have to remember one thing. That is, remember all octal symbols as well as hexadecimal symbols in terms of the binary format. That is very important. So, let me again simply recap that also. Okay. First, octal symbols in terms of binary format. Next, again, hexadecimal symbols. Hexadecimal means base is 16. In terms of binary format. So here we are always going via binary format and hence you have to convert all the symbols in terms of binary format. Okay. In octal, what are the symbols? We have 0, 1, 2, 3, 4, 5, 6, 7. These are the 8 symbols we have. Octal means base 8. So we represent each of these octal symbols in terms of 8 means 2 power 3. So we represent each octal symbol in terms of 3-bit binary format. So symbol 0 is basically 000. 1 means 001. 2 is equal to 010. 3 is basically equal to 011. 4 is 100. 5 101. 6 110. 7 is 111. Okay, so this is what we have. And for hexadecimal, first half exactly same. We have symbols as what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after that we have A, B, C, and then lastly D, E, F. Okay, so these are the 16 hexadecimal symbols we have. So hexadecimal means base is 16 basically here. Base value is 16. 16 is equal to 2 power 4. So we are writing each hexadecimal symbol in terms of 4-bit binary format. So in 4-bit binary format, okay, what are the binary equivalents? 0 means all zeros, 4 zeros, 1 corresponds to 0001, 2 corresponds to 0010, 3 corresponds to 0011, 4 means 0100, 5 corresponds to 0101, 6 0110, 7 is 0111. So if you notice, the first half is exactly same as the previous case. Only thing is we are writing this in terms of 3-bit format, and there we are writing it in terms of 4-bit format, and the fourth bit is always 0 here. Okay. And then next 8. 8 is 1000. 9 is 1001. A means value 10. After 9, 10 comes. So value is 10. So hence 1010. B is equal to 1011. C is equal to 1100. D is 1101. And E 1110. Lastly, F corresponds to 41. And I suggest that you guys remember these numbers. Okay. That is all these octal as well as hexadecimal symbols. If you remember, it becomes very easy for you whenever you have a base conversion problem when both bases are powers of basically 2. Okay. So let us solve a few questions on this topic. Yeah. So here if you see the question is, it was a pretty recent question, computer science GATE 2010 question. We have been given some equation. And in this equation, the base value is unknown. So base value R is unknown value. And ultimately, we are supposed to find out this particular unknown value R. So whenever you have this kind of a question where you have LHS equal to RHS. Okay, so this is a standard model where LHS is equal to RHS. So in this case, the only mantra, the only procedure is find out the values on both sides. Okay, so simply find out the values on both sides. You will get your answers. Okay, so let's solve this. So we have 124 base R whole power half. Square root means whole power half is equal to 13 base R, right? So we can square on both sides. When you square on both sides, you get 124 base R is equal to 13 base R whole square, right? This is what we have. And here, simply find out the values on both sides. Like I've told, the only mantra is find out the values on both sides. So what is the value here and here? Values on both sides. So we know how to find out the value. We have to use that weight formula. And by using the weight formula, what is 124 base R? This is simply R square plus 2R plus 4, right? 1 into R square, 2 into R, 4 into R power 0. R power 0 is nothing but 1. And what about RHS? RHS. What is 13 base R? 1 into R plus 3 whole square. So this is what we have. Now you have an equation. Solve this equation, you will get the value of R. That's it. A simple procedure. Okay. So let's solve the equation. R square plus 2R plus 4 is equal to R plus 3 whole square is R square plus 6R plus 9. And R square is gone. So when you rearrange the terms, then what do we get? So I think we are getting a negative answer. So R square plus 2R plus 13 R plus 3 whole square. So please let me know if I've done a calculation mistake anywhere here. So this is so yeah, we'll get here. Is there any calculation mistake I've done? Square plus 2R plus 4, correct. R plus 3 whole square is R square plus 6R plus 9, correct. So R square is gone, and then we send this to the other side, and we are getting some negative number, unfortunately. We're getting some negative number. So if I solve this, so we get here, yeah, 2R minus 4R becomes equal to 9 minus 4 is what I'm getting. So it shouldn't be the answer. There is some mistake I've done probably somewhere. I'll come back to this question shortly, guys. I think I've done a small mistake in writing the question probably. I'll come back to this question. Okay. So we have other questions on the same model anyway. So this is again instrumentation question, gate question only. We have 24 plus 14 is equal to 41. Again, we have some kind of LHS is equal to RHS. We have some LHS here is equal to RHS. So again, the procedure is find out the values on both sides. Okay. So simply find out the values on both sides. All we have to find out is nothing but the base value. So you simply have to find out what is the base value of this particular arithmetic operation. So since base is unknown, I'll write the base value here as nothing but b. Okay, so base value is unknown, base value is nothing but b. So now when you simply find out the value, what is the value of 24? Value of 24 is nothing but 2b plus 4. Okay, and what is the value of 14? The value of 14 is nothing but b plus 4. Okay, so we have converted LHS in terms of value. So this is basically value of 24. This is basically value of 14. RHS we have 41, which is 4b plus 1. Okay, so this is the value of RHS 4b plus 1. Do the calculation we have now. 3b plus 8 being equal to 4b plus 1. So if you rearrange the numbers, we get simply b is equal to 8 minus 1, which is nothing but 7. So in this case, in this problem, the base value is nothing but 7. So same kind of procedure we are supposed to use for the previous question also. Probably there was some data mistake that I have taken. Okay, I'll verify that and I'll rectify it. Okay. So the answer for this is nothing but 7. Okay, simple question. Whenever you have been given equation, all you have to do is equate the values of LHS, RHS. Okay, remember, equate the values of LHS as well as RHS, nothing else. Okay, next. Yeah, again, here also we have an equation and we are supposed to find out the number of possible solutions for x and y. So here we have two unknowns, x as well as y, and we are supposed to find out the values of both of these unknowns. Okay, or at least the possible values of both of these unknowns. So we have to find out, yeah, combination of what are the possible combinations of x and y. We have got these kind of questions twice in previous years of GATE. A good question, usually asked for either 2 marks or 1 mark, depending on the complexity of the question. Okay. So yeah, again, like I've told, what we are supposed to do, simply equate the LHS as well as RHS. You get one equation. What is the equation? 123 base 5, base is 5. So 1 into 5 square plus 2 into 5 power 1 plus 3 into 5 power 0. RHS value is simply, see here x is the symbol. So x into base power y power 1 plus 8 into y power 0. Okay. So we will get the equation first. What is that? This is 25 plus 2 into 5 is 10 plus 3 into 5 power 0 is 1, 3. RHS, what do we have? This is xy plus 8. We have xy plus 8. Now here LHS 25 plus 10 plus 3, 35 plus 3, 38. So we have LHS as 38. 38 is equal to xy plus 8. So means we've got xy being equal to 30. Okay. So we have got xy being equal to 30. So we got the equation first. Okay. We got the equation first. Now I will get two inequalities on the basis of one of the logic that we have discussed earlier. That is nothing but base value has to be always more than symbol value. Okay. So base is always more than symbol. This is one logic that we have. On the basis of this, if you look at this equation, what we can write? Base value is y. So y has to be more than first symbol x. Y has to be more than second symbol y. So y value has to be more than x. Y value has to be more than 8. So we have got two inequalities, one equation. Now on the basis of this equation, let us see what are the possible combinations of x and y. So I'm verifying what are the possible combinations of x and y in such a way that xy product is equal to how much? Always 30. Okay, always 30. Let us start with x value 1. When x is 1, what is the value of y? Product of xy has to be 30. So y value has to be 30. And please mind, both x and y has to be integers. That is one nice logic we have. So when x value is 2, what is the value of y? Y value is obviously 15. 2 into 15 is 30. When x is 3, what is the value of y? 10. When x is 4, y value is 7.5, not possible. So because which y equal to 4 is not possible. So y equal to 4 is not possible. Okay. So then what is the next one? 5. When x is equal to 5, 5 into 6 is 30. So y value becomes 6. That's it. All you have to do is calculate for one half. Second half is simply the reverse of the first half. Okay. So next, what we have is, yeah, x value is 6, y value is 5 reverse. X value is 10, x value cannot be 7, x value cannot be 8, x value cannot be 9, and so on. Next, x value is nothing but 10, then y value is 3, x is 15, y is 2, and x is 30, y is 1. So these are the 8 combinations of xy we have got, which satisfies xy product to be equal to 30. Now we will use these inequalities and verify in how many cases these inequalities are satisfied. First, y value has to be greater than 8. So whichever is not greater than 8, we will remove that. So if you notice in all these cases, okay, in all these cases, the value of y is not greater than 8. Okay, y equal to 6, 5, 3, 2, 1. They are not definitely greater than 8. So we are removing this entire part of the table. Okay. Now if I take the first 3 rows of the table, yes, these first 3 rows are satisfying all the conditions. What are all the conditions? The conditions are xy being equal to 30. First condition satisfied. Next condition, x should be less than y. Is it not true? Yes. 1 is less than 30, 2 is less than 15, 3 is less than 10. So x value is definitely less than y. And then y is greater than 8. Okay, so all these 3 conditions are satisfied. So means how many possible solutions we are having? We are having in this problem 3 possible solutions. Okay, 3 possible solutions. So look at the logic in this question. What is the logic in this question? Simple logic. Whenever we have an equation, equate the values of LHS, RHS. First thing. And second thing, yeah, use the logic that base value has to be always greater than the individual symbol values. That's it. These 2 topics we have combined and we have got the answer. And in this problem, how many possible solutions we have? 3 possible solutions for x and y. Okay, a simple question, not at all tough question. And please mind, this was a 2-mark question that was asked in GATE earlier. Okay. Next, we'll go for the next question. Again, same kind of question. If you notice, so we have an equation given, and we have x unknown, y unknown, 2 unknowns given, and we are supposed to find out the total number of possible solutions. These 2 questions were asked in computer science paper, so there is always a possibility of the same question being asked in either instrumentation or electrical or EC papers. Okay, so let's solve it by using the same procedure as compared to earlier. Yeah, so equate the values. So we get 4x plus 3 becomes equal to how much? Y into 8 plus 3. Okay, this is what we get. Now, whenever we I can cancel out the 3's here on both sides. So whatever 3 here is gone. So ultimately, I got one equation. That equation is nothing but 4x is equal to 8y, or simply x is equal to 2y. X is basically equal to 2y. So this is one equation we got. And furthermore, we can also write the inequalities. What are the inequalities on the basis of both of these equations? The inequality logic is very simple. Base value has to be larger than symbol. Okay. On the base value has to be greater than symbol. Base value in the first case is nothing but x. So x is greater than 4, x is greater than 3. So it has to satisfy both. So we'll pick the largest one, obviously. The largest symbol is nothing but 4. So x should be greater than 4. So this is the first inequality we got. And then the second inequality is nothing but base value here is nothing but 8. 8 should be greater than y, or y should be less than 8. So this is the second inequality, that y has to be less than 8. Okay, so let's start taking the numbers. So, x comma y values. Let's take x comma y values. So x as well as y, we'll take both combinations. We'll have to start somewhere. So I'll start by taking the value of x to be equal to 1. Y value to be equal to 1. When y is 1, x is equal to basically 2y, always double of y. So x becomes equal to 2. And then y is equal to 2, x value is equal to 4, 3, 6, 4, 8, and so on. If you take 5 here, 10. Okay, maybe 6 here, 12, and so on. Now let us take the conditions. The conditions are what? X has to be greater than 4. So since x has to be greater than 4, we can remove one part of this table. X is greater than 4 means x even cannot be equal to 4. I'll remove the first two rows. Because in the first two rows, as you can see here, x is not greater than 4. So I'm removing the first two rows. Next, y value, if you notice, has to be less than 8. So I can still further extend this particular, table in fact. So next, if you take y value 7, 14 here, y value 8, and then 16 here, and so on. We can further extend this. But the thing is, the bottom half of this table again I can remove. Okay, this part I can remove because in this case, y value is not less than 8. Y value is not less than 8. So only in the middle portion, if you notice, in this portion, we have all the inequalities and equations being satisfied. What are they? That is nothing but, x is equal to 2y, satisfied. Next, x is greater than 4, satisfied. Next, y is less than 8, satisfied. Okay, so we have all these three equations as well as inequality satisfied. So total how many solutions we have? 1, 2, 3, 4, 5. So we have overall 5 solutions. Again, here also what is the logic? The logic remains same as compared to the previous case. Find out the values and then use the logic that base value has to be greater than symbol. That's it. Okay. Yeah, let's go for the next question. So this is a good question. Okay, a very logical question. So if you use logic, hardly this will take a few seconds time. But if you use the brute force method, that is converting that number into decimal format and doing the calculations, it will take a lot of time for you to do the calculation. Probably some 5-6 minutes of time or more, and there is a lot of calculation involved. Okay, so we'll verify what is the logic here. We have to find out the number of ones in the binary representation of some calculation we have been given. Okay, but what is the number? What is the number given? If you look at the numbers, we have 256 here, we have 16 here. That should give you some logic. What is 16? I can write the 16 as nothing but 16 power 1. And the 256 is basically 16 square. Okay, that should give you an idea that probably this is some kind of power of 16. What is the next power of 16? We have 16 power 3. And indeed, 4096 is 16 power 3. Okay, so we have 16 power 3, 16 power 2, 16 power 1. Nothing is there here. So means I'll take into 1. This is basically into 1. If I take this as into 1, this portion, that 1 can be written as basically, that 1 can be written as 16 power 0. 16 power 0. So means we have basically a value. This number that is given to you is basically a value. Okay, so whatever, this entire number that has been given to you is basically, okay, so this entire number is basically a value. Value of which number? Value of which number? Since we have all, these numbers are 16 power something, means base value is nothing but hexadecimal. Okay, so in this case, definitely the base value is hexadecimal. Okay, 16. So in hexadecimal number system, what are the symbols we have? The symbols are 0 to 9, A to F. Okay, so let's look at the values. Let's look at the values of the coefficients of these weights. So we have the first value as nothing but 3. The symbol is also 3, obviously. Here we have the value as nothing but 15. 15 is the value of a symbol called as F. So this is basically F. Okay, and then this is 5, also 5. This is 3. The symbol is also obviously 3. Values and symbols, if the base value is less than or if the value is less than 10, symbol as well as its value both are exactly one and the same. Okay, so what is this guy right now? Okay, so this is basically value of a number called as 3 here, symbol F here, 5 here, and then lastly 3 here. Okay, that's it. We have got the hexadecimal representation of the given number. Now what we are supposed to calculate once in the binary format. So we have to convert that number into binary format. So can we not convert this number into binary format? Yes. How do you do the conversion? Like I've told, if the base value is a power of 2, you can directly convert each symbol into binary format. In hexadecimal representation, what is 3? 3 is basically 0011. What is F? 1111. And what is 5? 0101. And what is 3? 0011. That's it. So we have got the binary format of the given number. So since we have got the binary format, we can count the number of ones directly. How many ones we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total number of ones we have here. Okay, the total number of ones we have here is equal to 10. That's it. So we have used logic and we have understood that, okay, the given number actually is the value of a hexadecimal number, and that particular hexadecimal number is represented as symbols, and those symbols are converted into individually binary format. We have got the answer here. Okay, I hope this is clear. Very simple question if you use logic. Okay. Yeah, next again, this is a pretty recent question, 2021 question if you notice. So we have x and y, two decimal digits. So x is a decimal digit and y is also another decimal digit. Okay. X as well as y are two decimal digits. And yeah, these two guys are decimal digits basically. And they are the decimal digits of the binary number, when expanded into decimal format. The binary number given to us is 01101, and then we have to find out what is x plus y. Very simple question again. All you have to do is we have some equation. Whenever we have an equation, what is the logic? Convert things into value. Whenever you convert the numbers into value, you get the number in terms of decimal format. RHS already is in decimal format, so I don't have to convert the RHS. All I have to do is convert only LHS into its value. Okay, so convert the LHS into value again. So whenever you convert this LHS into value, this is fractional part. In the fractional part, how do you take the weights? We'll take the weights as negative powers of 2. So the first number is nothing but 1. So 1 into 2 power minus 1. Next digit is 1 again. 1 into 2 power minus 2. Third digit is 0. So 0 into 2 power minus 3. The last digit is 1 again. 1 into 2 power minus 4. So do the calculation. What do we get? 2 power minus 1 is 0.5. So this is 0.5 plus 1 by 4 is 0.25. This is 0.25 plus 1 by 8 is basically 0.125, but rather this weight is nothing but 0, or the number is nothing but 0. This is gone. This value is 1 by 16. 1 by 16 is half of 0.125. Half of 0.125 is 0.0625. So let us do the calculation here. Whenever you add the numbers, we get here 0.75 plus 0.0625. When you add the numbers, you get 0.8125. Okay, so this is the number you get. And the result is always obtained in terms of what format? Decimal format, because values of any number system is always obtained in terms of decimal format. So I got 0.8125. So compare both of these equations, or compare both of these numbers. Okay, this number compared with this number. When you do the comparison, please observe leftmost digit is 8 matching for us. 8 here. So 8 here, 8 here matching for us. Last number is 5 matching for us. So means, yeah, we have done the problem properly well. So there is no calculation mistake that is involved. We have to find out the middle two numbers. So the middle two numbers will be what? X will be equal to 1. So on the basis of this, X is 1. And the value of Y is equal to how much? 2. So Y is equal to 2. Okay, so we have got X1, Y2. So what is X plus Y? X plus Y now is simply, 1 plus 2. 1 plus 2 is how much? It is nothing but 3. So please notice, it was a pretty recent question. Okay, in the pretty recent question also, the kind of question that we have is exactly the same. That is nothing but find out the values, you will get your answer in case of number system based conversion problems. Okay, and not a tough question. if you know the logic, hardly this question will take maybe 40, 50 seconds of time, less than a minute of time, not more than that. Okay. Yeah. Let's go for the next question. Yeah. This is another new model question, I would say. Slightly, we have an extra concept to learn here. So we have been given a P, a number called as P, and this number P is basically a 16-bit number. This is a 16-bit signed number. We have to, since we have started with signed numbers, we have to again slightly recollect this concept of signed numbers. So I'll do the recollection first. Yeah. So in case of signed numbers, we have three types of signed numbers. So the first type of signed numbers we have is sign and magnitude format. The first one is the sign as well as magnitude format. Okay. And the second one is ones complement format. And the last one is two's complement format. We have the two's complement format of numbers. Okay, three types of signed numbers. In all the signed numbers, one logic remains same. That is nothing but leftmost bit represents sign bit and the remaining bits represents magnitude bits. Okay, so common thing is nothing but leftmost bit basically represents sign bit. Yeah. So let's assume the number is dn-1, dn-2, and so on, d2, d1, d0. So in this n-bit number, which is a signed number, let's assume, so the leftmost bit corresponds to always the sign bit, always. And the remaining bits that you have will be called as the magnitude bits. Okay. And furthermore, whenever this sign bit is equal to 0 or is equal to 1, yeah, sign bit can take only two values, either 0 or 1. Whenever the sign bit is 0, in this case, number is positive. And whenever the sign bit is nothing but 1, so in this case, number is negative. So this is true in all the three cases, common thing. No change with respect to the sign bit in sign magnitude format, ones complement format, or two's complement format. Okay. So let us now see how to convert that number from, let's assume, decimal to sign magnitude format or ones complement or two's complement. So now we'll discuss about decimal to simple logic. This is also signed number format. Okay. So we'll discuss all three in one single go. We'll discuss all the three formats in one single go. Let's assume I have been given a number n to the base 10, which is a signed number right now. Okay. So let's assume the number is n to the base 10 is nothing but negative. Okay. So in this case, the sign bit s becomes equal to 1. And if n to the base 10 is positive, so in this case, sign bit s becomes equal to 0. The leftmost bit is either 0 or 1. Okay, so this will give us the leftmost bit. So the sign bit discussion is complete. Now let us come to the magnitude bits. That is where the difference comes in all the three cases. Okay. So what we do is nothing but now we take the magnitude of this particular number, magnitude of n to the base 10. So first we convert this n to the base 10 into true binary format. Okay, so first we are converting this into true binary format. Okay. So if you simply convert that numbers into true binary format by using the repeated division process, so in this case, this becomes equal to the magnitude bits in case of the sign and magnitude form. So this is basically equal to the magnitude bits, where in case of sign magnitude form. The first form is basically sign magnitude form, and the true binary form becomes equal to the magnitude bits in case of the sign magnitude form. Next is replace ones with zeros and zeros with one. So ones replaced as zeros and zeros replaced as ones. So now you get some other number. That some other number is called as complement format. We call it as nothing but complement format, or basically ones complement format. To be more precise, we call it as ones complement format, or in general we can also call it as complement format. And this becomes equal to the magnitude bits. This becomes equal to the magnitude bits in case of ones complement format. Please mind that in all these cases, this will give you only the magnitude bits, the second classification. Now here, whenever for the previous answer, whenever you add one to the ones complement representation, you get the twos complement representation. So we call it as nothing but twos complement representation, or simply twos complement format of the number. Okay. And what is this right now? This is basically the magnitude bits in case of the twos complement format. Okay. So see, in one single slide, we have explained how to convert the decimal number in terms of the sign magnitude format, ones complement format, as well as twos complement format. The logic for sign bit remains the same. So this basically is nothing but the sign bit. So the logic for sign bit in all the three cases remains same, but the logic for magnitude bits changes from format to format. In the sign magnitude format, the magnitude bits basically are true format of the magnitude, and in ones complement format, it is a ones complement of the true format, and in twos complement format, it is ones complement plus one. Okay, so if I want twos complement representation, I have to go through this entire process. Okay, if I want ones complement format, I'll stop here. If I want sign magnitude format, I'll stop here. So the simplest of all the methods is sign magnitude format for representation. But for analysis, the simplest format is always twos complement format. So later on, we will discuss that. Okay. Yeah. So next we'll go for the reverse. The reverse, which is basically converting the sign magnitude number or ones complement number or twos complement number into the decimal format. That is, we'll discuss here the signed binary number into decimal format. Okay. So in this case, the very first thing you do is look at the leftmost bit. Okay, leftmost bit is basically sign bit. Leftmost bit is sign bit. Okay, and whenever the sign bit is equal to 0, means number is positive. And whenever sign bit is basically 1, so in this case, number is negative. Okay. So now, what you are supposed to do with remaining bits, that depends on whether the number is positive or negative. Okay. So now, let's go for the remaining bits. Look at the logic here. Okay. So in sign magnitude format, first in sign magnitude format, we'll see, and after that we look at in ones complement format, and then we'll go for in twos complement format. Okay. So in sign magnitude format, what we do is we simply find out magnitude as nothing but, what is the magnitude here? Magnitude is basically value of remaining bits. So whatever remaining bits you have, if you simply find out the value, you get it as nothing but magnitude in case of sign magnitude format. In case of ones complement format, what is magnitude? So magnitude is basically value of complement of remaining bits. Value of complement of remaining bits. So you have two steps to do here. What are the two steps? First is you have to complement the remaining bits. and then find out the value of the remaining complement of the remaining bits. What about in case of 2's complement format? In case of 2's complement format, same as the previous case, value of complement of remaining bits plus 1. Okay, so apart from the previous step, what you have to do is add 1. So this addition of 1 is very important in case of 2's complement. You have to add 1 to the value of complement of the remaining bits. Okay, so this is how you convert the given signed number in terms of decimal format. Okay, and whatever drama you are doing here, this is only for negative numbers. Okay, so this difference that you have is only for negative numbers. For negative numbers. Okay, that's it. This is only for negative numbers. Whatever complementation we are doing here, only for negative numbers. So then what about positive numbers? For positive numbers, it is very, very simple. Okay, so let's assume you have positive numbers. For positive numbers, I don't care what format you take. That is, in case of sign magnitude format, 1's complement format, as well as also 2's complement format. In all these three cases, for positive numbers, magnitude is simply equal to value of remaining bits. Value of remaining bits. Okay. So understand, this is one logic that you have in case of positive numbers. For positive numbers, it's very simple. I don't care whether the number is given in terms of SM format, 1's complement, 2's complement format. The magnitude bits or magnitude is basically the value of the remaining bits by removing the sign bit. When I say remaining bits, no, I mean to say the bits after removing the sign bit as such. Okay. Yeah. So this is about the conversion of numbers from both decimal to signed numbers to decimal numbers. There is one very important property in case of 1's complement as well as 2's complement numbers, that is known as sign bit extension. That is basically sign bit extension. Very, very important property. We have got good number of questions on this topic earlier. Okay, either directly or indirectly. Okay, on the basis of sign bit extension. As the name itself says, what is sign bit extension? Extending the size of the number by using sign bit. Okay, so this is basically extending the size of the number by using sign bit. But this method is applicable only in case of 1's complement as well as 2's complement format. Okay, so this is basically applicable in 1's complement as well as 2's complement format. Okay, but not applicable in case of, but basically this is not applicable in case of the sign and magnitude format. Okay, it is applicable only for 1's complement as well as 2's complement format, right? Next, the beauty of this is nothing but whenever you see a continuous string of 1's on the left side of the number, okay, in case of 1's complement or 2's complement, you can replace it with negative sign. Okay, so here a continuous string of okay 1. Okay, and this continuous string of 1 is basically equivalent to negative sign. Okay, and whenever you have a continuous string of zeros, that is equivalent to a positive sign, where in case of both 1's complement as well as 2's complement numbers only. Okay, so this logic is applicable only in case of 1's complement as well as 2's complement numbers. See, notice one thing, you are not extending the size of the number by using 0. You are extending the size of the number by using sign bit here. Okay, sign bit is being used in the extension of number. So what is the sign bit in case of negative numbers? It is nothing but 1. So you extend the size of the number by using 1 in negative numbers. You extend the size of the number by using 0 in case of positive numbers. Okay, so this is the logic that we have in case of the sign bit extension. So let us look at a few problems on this particular topic right now. Okay. Let's start with an easy question. This is one easy question that you have, which combines two things. Conversion of numbers, decimal number basically, into binary format, signed binary format, and also the concept of sign bit extension. Both concepts we are using here. So here, if you notice, the number is minus 28. The number is negative, right? So number is basically negative. So whenever the number is negative, what is the sign bit now? The sign bit becomes equal to 1. So we have obtained the sign bit now. One task is done. Then what is the second task? The magnitude. What is the magnitude of this number? Magnitude of this number is nothing but 28. Okay, and the number is 2's complement number. And we have negative number or positive number? We have negative number. So what is the procedure? What is the procedure in case of negative numbers? Let's verify. Yeah, decimal number to sign bit number. If I have a 2's complement, if I want the magnitude bits in case of 2's complement number, first I have to obtain the true binary format, do the 1's complementation, add 1 to it. So these are the 3 steps we are supposed to do. Find out the true binary format, complement the numbers, and then add 1. Why? Because the number is nothing but negative number. Okay, the number is nothing but negative number. And I'm sorry, I forgot to mention. Okay, I'm sorry, I forgot to mention. This procedure, you will use it only for negative numbers. Okay, only for negative numbers. I'm sorry, I forgot to mention. What about positive numbers? For positive numbers, what we basically do is nothing but magnitude bits are basically true binary format only. True binary form of the number or magnitude 10 to the base 10. That's it. So we don't do any complementation if the number is positive number. Whatever complementations we have, we will do it only if the number is negative number. Okay. So this entire logic is only for negative numbers, not for positive numbers. For positive numbers, yeah, no matter what format you take, sign magnitude format, 1's complement format, or 2's complement format, in all the 3 cases, we simply take the true binary format of that particular number. Sorry, I forgot to mention earlier. Okay. Yeah. So anyway, the number is negative number. So what is the procedure for us? Let's go back to the question now. Yeah. So this was the question. So since the number is negative number, what we have to do is nothing but find out the true binary format of this. Step 1. Okay. So true binary format. So how do you obtain the true binary format? Repeated division process. So I'll take 28, divide that number with 2. What do we get? 28 by 2 is nothing but 14. Remainder is 0. And nicely I know already what is binary format of 14. What is the binary format of 14? 1110. Okay, that's it. I got my true binary format. What is the true binary format of 28 now? It is nothing but 11100. Okay, so 28 right now, 28 in true binary format, is basically 1110. Next step, complementation. So 1's complementation is basically replacement of 1's with 0's and 0's with 1's. So hence we'll have 0011. I've replaced the first 3 1's with 0's and last 2 0's with 1. And then lastly, add 1. When you add 1 to 0011, basically you have 1 1. 1 1 plus 1 is basically 100. Okay. So we get the answer as nothing but here 0 0 1 00. So this is what we have regarding the magnitude bits. Okay, so now we have got the magnitude bits. These are the magnitude bits. Okay, and what is the sign bit? Sign bit is nothing but 1. Combine both of them. So when you combine both of them, so I can write right now minus 28 as nothing but, so minus 28 in 2's complement format to be equal to sign bit is nothing but 1. So leftmost bit is 1. What are the remaining bits? Remaining bits are 0, 0, 1, 00. Okay, so look at the answer. We have got the answer in terms of 1, 2, 3, 4, 5, 6. 6-bit format. So we have got the answer in terms of 6-bit format. But the examiner want the answer in terms of what format? 16-bit format. So what to do? We extend the size of this number. Okay, that same number now. Please notice the concept we are using here. We are using the concept of sign bit extension. So we are extending the number from 6-bit format to 16-bit format. Okay, what is the original number? Original number is 100, 100. Okay, what is the sign bit? Sign bit is basically 1. So copy paste 1 to the left of the number. How many empty places we are having? 16 minus 6, 10. So 10 ones I will take. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so we have taken 10 ones here. So finally I've got the number. Okay, so what is the number right now? Group them into groups of 4 bits each. 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, and then we have 0, 1, 0, 0. That is the number. So let's verify the options. If you verify the options, anyway, see, nice thing is whenever you see this question, okay, straight away you can eliminate 2 options. Number is negative, means leftmost bit is obviously what? Leftmost bit is 1. So C is not the correct answer, and same way D is also not the correct answer. Sorry, C is not the correct answer. D can be the correct answer probably. Okay, so I could remove C. I can eliminate one option without even putting my pen on paper. Now, yeah, where we have this sign bit extension being possible in case of option B. If you look at the option 4 ones, and then 111, 0, 0, 1, 00. So we have the correct answer as nothing but B. So we have used here 2 concepts. The first concept is nothing but converting the converting the decimal number, signed decimal number into 2's complement format, and then extending the size of the number from 6-bit format to 16-bit format. So initially don't bother about how many bit format the question is given for you. Get the answer in terms of either 6-bit format, 5-bit format, depending on the number given to you. So first find out that number and then extend the size of the number by simply copy pasting the sign bit to the left of your original number. Okay? Yeah. So let's go for the next question. Yeah, again, this is a question of sign bit extension. So we have 3 numbers given. So let us see what these numbers are. The first number is 11001. The next number is 1001. And the last number is 111, 111001. Okay. And all the numbers are given in terms of 2's complement format. All the numbers are given in terms of 2's complement format. So we can use the logic of sign bit extension here also. Okay. Please notice that continuous string of ones. Whenever you have a continuous string of ones until the first 0. So I have 2 ones here. What do they indicate? They indicate simply the number is negative. Here I'm having only 1 1. That 1 1 also indicates what? That the number is negative number. Here I have 3 ones. What are the 3 ones indicates that the number is negative number again. So I can remove all the numbers and say that okay, they indicate simply sign. What is the sign? Negative, negative, negative. Okay. And all the numbers are given in terms of 2's complement format. Now look at the magnitude bits in all the 3 cases. Is it not same? Yes. Here also, in all the 3 cases, we have 0001. Means definitely all the 3 numbers are one and the same. Okay. All the 3 numbers are same. Basically. Means nicely you can eliminate at least 2 options. I can remove option, A as well as option D. Both of them can be removed. Because I don't have same numbers. Numbers are not same in both A and D. Means I can say that they are not the correct answers. So answers can be either -6 or -7. So I have to find out the magnitude. I know that already numbers are negative. Okay, numbers are surely negative, 100% for sure. But what is the magnitude of these numbers? So to find out the magnitude of 2's complement numbers, what is the procedure we have? The procedure we have is nothing but first step, find out the complement. Okay, complement. So when you complement 0001, what do we get? We get 110. Find out the value. What is the value of 110? It is 6. And then add 1 to it. Okay, simply add 1 to it because the numbers are given in terms of 2's complement format. So we have got the magnitude as nothing but 7. So this 7 corresponds to the magnitude right now. Okay, that's it. We have got the answer. What is the answer now? Minus 7. So overall the answer is nothing but basically now minus 7. And hence C is the correct answer. So now whatever is the first number given to me, 11001, next 1001, and then we have 111001. So what are these guys right now? Okay, now can you tell me what are these numbers? Yeah, what are these numbers? These numbers basically are, the first one is 1, 2, 3, 4, 5. I have 5 bits here. So this is basically 5-bit representation of minus 7. The next one is basically 4-bit representation. Look at the numbers. All are basically minus 7 only. And the last one is basically 6-bit. We have 6 bits here. So this is basically 6-bit representation of the number minus 7. All of them corresponds to minus 7 where? In case of 2's complement format. Okay, so this is corresponding to 2's complement format of representation. Okay, but rather all the numbers are basically minus 7 only. Again, this is a question of simply sign bit extension. Okay, good question, simple question. So, very less calculations you are supposed to do. Again, instrumentation, very old question, but still nice logical question. Okay, so you have one number. And what is this number? This is basically a 2's complement number. This is basically a 2's complement number given in terms of 4-bit format. This is a 4-bit 2's complement number. And what is the number? The number is x3, x2, x1, x0. The important bit is nothing but x3. What is x3? Leftmost bit. What is the leftmost bit now? This is sign bit. Okay. Why do we require this sign bit? Because the examiner is asking that, okay, boss, how do you store this number in terms of 8-bit format? How do you extend the size of this number? So basically you have to extend the answer in terms of 8-bit format. What do? I take the original number. See, in the first option, what this did was they extended the size of the number by using zeros. No, not the correct answer. We don't extend the size of the number by using zeros or one. Okay, we don't extend the size by using either zeros or ones. We can't fixate that. We extend the size of the number by using only sign bit, and the sign bit can be either 0 or 1. Okay, so there are both possibilities. There can be this kind of a possibility. There can be this kind of a possibility, but that depends always on the sign bit, which is here x3. So if you look at this option is correct option. Okay, so this is our original number. Left of original number, we are using what? The sign bits. So what are we using here? We are using here the sign bit extension. What did you take in the last option? The last option you have taken complement of sign bit, which I obviously don't take in case of sign bit extension. So definitely D is wrong answer. Okay, the only correct answer we have is basically C. Okay, so C is the only correct answer we have. Right? Again, this is a question of sign bit extension. So whenever you look at a question, you have to identify, okay, the question is basically from what topic. Okay, so that is something that you have to identify in the beginning itself. Okay, and this question is basically on the basis of range. Okay, so this is basically a range based question. Okay, range based question. Again, let's go back to the, okay, let's complete the other questions first, and then we can go back to this. Let's complete the other questions. Yeah. Okay, so here there is a question. Try to answer this question. This is a good question. This is basically a good question. Try to answer this question. One of the nicest questions that I've seen, in GATE exam. Simple question, yet a logical question. So here we use one, extra logic that I have a binary number n, okay, n to the base 2. Whenever you multiply this number n to the base 2 with 2 power, let's assume r. So whenever you do this is basically equivalent to placing zeros to the right of the number. Okay, you have the number n. So simply place zeros to the right of the original number. Okay. So how many zeros you're adding here? The number of zeros here is equal to the value of r. So here you are placing r zeros. Okay, so you are placing r zeros. This is the logic. Basically, if you do that same thing in case of your decimal also, in decimal it's pretty clear for you. If I take, let's assume 98 into 10 square. Let's assume 98 into 10 square. What is the answer? If I ask you what is 98 into 10 square, you will simply say, sir, this is 9800. So what did you do? To the right of original number 98, you have placed 2 zeros because this is 10 square. If I have taken 10 cube here, you will take 3 zeros here, right? Yes. Why? Because this is entirely in terms of base 10. So 98 base 10 into 10 square is equal to 9800. Same logic is also applicable in case of base 2. N to the base 2, some number in base 2 into 2 power, base power r. Here also you have taken 10 square means base power r is equal to original number to the right of original number, you will place simply zeros. Okay, so this is the logic that we have here. Okay, same logic we are using in this question also. Okay, what was the number p? P is given as p is equal to so p is a 16-bit number and p is basically equal to in hexadecimal format base 16 number f 8 7 b, and this is given in terms of base 16. But if you see, you are multiplying this number with 8. What is 8? I can write 8 as nothing but 2 power 3. So please notice, base power 3 is what you are supposed to take, 2 power r. So what you have to do is convert this p also in terms of p to the base 2. So means you have to obtain the binary format of this number. Hexadecimal to binary is very simple, right? What is the logic in hexadecimal to binary? F means 4 ones, 1 1 1 1. Okay, and then 8 1 0 0 0. 7 corresponds to 0 1 1 1, and 3 corresponds to 0 0 1 1. Okay, and this is now taken in terms of binary format. So I got my answer in terms of binary format. Now what I am doing? So this is the step 1, converting the p base 16 into p base 2 format, binary format. What is the step 2 now? The step 2 is nothing but convert 8 or multiply that number 8, p to the base to this number by using 8. What is this now? 8 is nothing but 2 power 3. 2 power 3 into p to the base 2. Okay, what do we get? Since we are multiplying this number with base power r to the right of original number, what is the original number? 1 1 1 1, 1 0 0 0 1 1, 0 0 1 1. To the right of original number, you are supposed to place zeros. How many zeros now? You are supposed to place 3 zeros. Okay, so you have to now replace, or you have to now place 3 zeros here because you have multiplied that number with 2 power 3. So this 2 power 3 multiplication results in these 3 zeros. Okay, what is the next step? The next step is nothing but write the result in terms of, again, hexadecimal format. All the options, if you notice, are given in terms of hexadecimal format. So how do you convert the given number into hexadecimal format? By grouping bits. So the grouping starts from where always? Right side. So this is one group of 4 bits each. This is another group. This is another group. And lastly, this is another group. Sir, what about the remaining 3 ones? I can discard these 3 ones. These 3 ones, if you notice, can be discarded. Why are we discarding them? Okay, since they are sign bits. So you have simply done reverse on sign bit extension. Okay. You are playing Uno and you have done reverse on sign bit extension. You have simply said, okay, let's not extend. You have trimmed the sign bits. I already have this 1 1. What this 1 1 indicate also? Sign bit only. So these two ones already indicate sign bits for me. So these two ones also indicate sign bits for me. Okay. Basically all these 5 ones indicate sign bit only. So I take 5 ones, 4 ones, 2 ones, 1 1. Doesn't matter. All of them indicate simply that the number is basically negative number, because we have ones means number is negative number. So if I take only 2 ones instead of 5 ones, it will not change the sign, right? Sign still remains the same. Magnitude will not change anyway. So because of that, instead of taking 5 ones as a sign bit, I can simply take only 2 ones as a sign bit. And I have got my answer. What is the answer right now? The answer is now convert each of the grouping into the corresponding hexadecimal number. 1000 means 8. And then we have 1001, 9. We have now 0011, 3. Lastly, we have 1100. 1100 value is 12. 12 means 10, 11, 12, A, B, C. So this becomes equal to C. Okay, so what is the answer now? So answer is nothing but C398. Okay, so look at the options. C398. Oh, okay, I think I have done a small mistake. Somewhere I have done a small mistake. 1 C3D, it should be D. F37B. Okay, sorry. This is not 3, this is B. My mistake. Okay, so this is not 3, this is B. B means 11. 11 means 1011. So this is 1011. Yeah, the answer is not mentioned means obviously I've done some mistake. 1011. So 1011 means this is basically 1011. This is basically 011. Okay, so 8 will not change. Remaining digits also do not change. We have 1101. 1101 value is 13. 13 in hexadecimal format is what? This is basically D. Okay, so you see, we understood that we have done a small silly mistake. D. So finally, what is the answer? C3D8. Okay, so now we have got the answer as nothing but C3D8 in terms of hexadecimal format. Okay, so the correct answer is nothing but A here. A simple question. Okay, so here we have used the concept of sign bit extension, and we have also used this concept that whenever you multiply a number n with some base power r, that is equivalent to adding r zeros to the right of the original binary number. Okay, we have used that concept also. And then reverse, we have converted the binary number also into hexadecimal. So hexadecimal to binary, and then multiplying that binary number with base power r, and then converting that result into back to again the hexadecimal format. So these are the 3 steps we have used logically. Okay. Okay. This is again a question where we have to convert the given octal number base 8 into hexadecimal as well as also into base 4 number. Okay. Not a tough question. I'll do at least one half of the question. What is the logic here? We have both bases as nothing but powers of 2. So in this process, don't convert that number into decimal. Converting that number into decimal will be a lengthy process for you. All you have to do is we have 1, 2, 3, 4, 5, 6, right? So this is given in terms of octal. Octal 8 means what? 2 power 3. So write each of the digits in terms of 3-bit binary format. Okay, so in 3-bit binary format, we have 1 as nothing but 001, 2 basically is 010, 3 is 011, 4 is 100, 5 is 101, and 6 corresponds to 110. Okay, so these are the digits we have. And now let's assume you want the number in terms of hexadecimal. What to do? Group the digits into groups of 4 bits each, starting from right side. Okay, so starting from right side, if I group the digits into groups of 4 bits each, this is one group, and then this is another group, and then we have this is another group. Okay, and this is another group. Lastly, we have another group. Empty places we have can be filled with zeros whenever there is empty place. Now what do we have? 1110 value is 14. 14 means E. Okay, 14 corresponds to E. We have 0010 corresponds to 2. 0 triple 1 7 1 0 1 0 10 10 means A. Okay, and all zeros corresponds to 0. We can discard 0 to the left of the number. Okay, so then what is the remaining number? The remaining number we have is A72E. So A72E, you have, yeah, definitely C is not the correct answer, D is not the correct answer. The answers can be either A or B. Answers can be either A or B. Now, next question is base 4 format. Okay, so how do you convert this number? Again, I'm taking this number, which is 1, 2, 3, 4, 5, 6. Number is given in terms of octal format, 2 power 3. We will write each digit in terms of 3-bit format. So doing that, you'll get 001, 010, 011, and then 100, 101, 110. Right? The number is given in terms of base 2 format. Now I want the next part of the problem. I want the answer in terms of base 4. What is base 4? 4 is equal to 2 power 2. Means now you have to group the digits into groups of 2 bits each. So this is one grouping, this is another grouping, and so on. Repeat the process. So grouping here, grouping here, grouping here. Okay, so repeat the process. So I've grouped all the digits. Now write the values of each. 10 value is nothing but 2. 11 means 3. 10 is 2. 00 is 0. 11 is basically 3. 01 1. 10 is 2. 10 is 2. That's it. We have got the answer. Last 0. You can neglect the last 0 anyway. Okay. So this is the answer we have got in terms of base 4. Okay. This is the answer in terms of base 4. So if you look at the options, 22130, 22130. Yeah, 0232, 023. The answer is nothing but A. Okay. A is the correct answer, which is matching both the hexadecimal as well as base 4 format. So remember that whenever both bases, the first base as well as the next base, both are powers of 2, you can always go via binary format. Don't go via decimal format. It will be a very, very lengthy process. Okay. Yeah. So this would be the last question of the day. Okay. Last question of the day. This was a very recent question, GATE 2020 question, 2 marks question. This was a 2 marks question. So in this question, you are supposed to find out something called as P plus Q plus R. Okay, so you have PQR, and all three guys PQR in binary format is equal to the number which is 1100. So this is the number of importance for us. Okay, but basically P is nothing but number in terms of sign magnitude format, and Q is equal to number in terms of 1's complement format, and R is equal to number in terms of 2's complement format. Okay. So what we have to do? We have to now perform some arithmetic operation P plus Q plus R. So to find out the calculation of P plus Q plus R, we have to find out the decimal values of PQR. So that is our first problem. Okay. So let's do the conversion now. First part 1100. If it is given in terms of sign and magnitude format. Next, 1100. If it is given in terms of 1's complement format. Next, 1100. Same number is given in terms of also 2's complement format. Okay, so that is what is given. Please notice. Consider that 1100 is given in terms of sign magnitude format, 1's complement format, and 2's complement format. Then P is the value in decimal format in sign magnitude number representation, and 1100 in case of 1's complement representation, decimal equivalent is nothing but Q. 1100, if it is given in terms of 2's complement format, the decimal value is R. Okay, so this is the given data. So then please find out in all these cases, what is the decimal value? In all these cases, all we have to find out is decimal value. So how do we do that? We always start with the leftmost bit. Okay, the very first thing you have to verify is leftmost bit. What is the leftmost bit here? 1. 1 as well as 1. Okay, so 1 means what number? Negative, negative, negative. So all the three numbers are basically negative numbers only. So since all the three numbers are negative numbers, so let's convert that numbers into the remaining bits. Remaining bits are what here? 100, 100, 100. So they are the remaining bits. So we have to find out the magnitude. So what is the magnitude in case of the sign magnitude format? Magnitude is basically value of 110. So you take 100, the remaining bits, and find out the value. And what is the value of 100? It is nothing but 4. So that's it. So on the basis of this, we can say that the number p is equal to, number is negative with a magnitude of 4. So p is equal to -4. Next, what is the remaining bits? Remaining bits are basically 100 base 2. So since the number is ones complement format, how do you find out the magnitude? So we have to first complement the remaining bits. Complementation of remaining bits is nothing but 100 complementation is 011, and then find out the value. What is the value of 011? It is nothing but 3. So means magnitude is 3. So q is equal to -3. Number is negative number. Okay. And last case we have 100 base 2. 2's complement representation. First we have to complement 011. Find out the value. Value is 3. And then add 1. When you add 1, we get value as 4. So means the value of r is equal to -4. R is equal to basically -4. So we are done with finding out the values of p plus q plus r. Okay, p plus q plus r is complete. Now what we have to do? We'll do the calculation. What is p plus q plus r right now? P is -4, q is -3, r is again -4, and when you add all the three numbers, what we get is -8, -3, -11. Now ultimately we have to represent the answer in terms of what format? 6-bit 2's complement representation. So we have to get the number in terms of 2's complement format. So the next step is basically convert this -11 into the 2's complement format. Okay, number is positive or negative? Number basically is negative number. So if the number is negative, sign bit is equal to 1, right? Yeah. What about the magnitude? What about the magnitude? The magnitude is equal to 10. Okay. So what are the magnitude bits now? The magnitude bits are, so let us take 10 in terms of true format. In true format, 10 basically is nothing but 1010. Complement it. In complementation format, we get 0101, and then add 1 to it. When you add 1 to 0101, you get 0110. That's it. I got my magnitude bits. Okay. So finally, what is -11? -11. Okay, -11 in 5-bit initially 2's complement format. 2's complement format. And by the way, what is -11? -11 is p plus q plus r. Okay. Okay. And what is the answer? Sign bit is basically 1. Leftmost bit is 1. And what are the remaining bits? Remaining bits are 0, 1, 1, 0. But examiner wants the answer in terms of 6-bit format. So what is -11 in 6-bit format? Sign bit extension. So by using the sign bit extension, what is the sign bit here? 1. So extend the size of the number by using 1. So this is 1, 1, 0, 1, 1, 0. Okay. So I copy pasted the sign bit to the left of the original number. This is the sign bit extension concept. So this is a very good question. Definitely a 2-mark deserving question. Okay. Wherein all the three concepts are tested in one single question. What three concepts of sign magnitude representation, 1's complement format, 2's complement format, and as well as converting the decimal number into again 2's complement format, and also sign bit extension. So you notice one question, 5 concepts are being asked. Okay. So very good way of framing question. Okay. So definitely a deserving 2-mark question. Good question, easy question, not a tough question, but rather you have to be careful, because even one silly mistake here may make your question wrong. Okay. So yeah, so this is regarding this session, today's session. So I hope the base conversion concept as well as also the sign number concept is clear for you. Okay, this is the basics of digital circuits. You should remember all the numbers starting from 0 to 15. Okay, 0 to 15 you should remember in the binary format. That is very basic because it will help you greatly in case of the K-map minimization, representation of Boolean function, writing minterms and maxterms, etc. Okay, so lot many people neglect number systems as you saying that okay, this is a very easy topic, no need to study a lot. But rather, if you are not comfortable with number systems, writing the binary number will become a huge burden for you. Okay, so I always emphasize on number systems. Easy topic that is, but still that will lay a very good foundation. It will increase your speed in exams also in digital circuits. Okay, yeah. So with this, I'll call it a day. Any doubts you have, please ask me in this session. Any doubts you have, please ask me. Okay, I have done a mistake. Double one. I think okay. The answer is not matching. 10 is 1010. Complement is 0101. Oh, sorry, magnitude is 11. No, oh, okay. I have done a blunder here. I'm sorry. See, this is a mistake. One small mistake you do, it will go wrong. So basically here we have magnitude 11. Magnitude is not 10. I don't know why I have taken 10. So 10 means, sorry, 11 means 1011, 1011. Complement is 0100. Complement is 0100. If you add 1, you'll get, if you add 1, you'll get 0101. Okay. And then, yeah, in 5-bit format, what is the answer? 5-bit format, you will get the answer as 010101. So, 0101. Okay, sign bit is nothing but 1. And if you extend it, you will get the final answer as nothing but 11. Sign bits basically. Magnitude bits are 0101 only. Okay. Yeah, I think this is matching with one of the option. 110101. So 110101. Yeah, option A is matching for us. Okay. Option A is matching for us. Sorry, small silly mistake I've taken. Okay. Yeah, so this is what we have regarding today's session. I'm sorry that I started today's session a bit late. There was a small technical issue. Okay, first day hiccup. From tomorrow onwards, you won't have the delay. Okay, we'll start the session on time at 7 o'clock sharp. Okay. Yeah, so please do revise this topic once again. Please practice these questions once again. Okay, very good source of questions, previous questions, because you have computer science questions in our PYQs book. So you have a largest set of questions for digital circuits. You have electrical, ECE, instrumentation, as well as also computer science questions. So I have done a few questions. You also solve the remaining questions so that all questions will be complete for you. Okay. And before coming to tomorrow's session, please do complete this remaining previous questions from the previous questions book that we have given you. Okay. Yeah. So any doubts you have, please let me know. I'll be happy to answer your doubts. Yeah, first question, I think there is a data mistake in that. I'll get back to that question in tomorrow's session for sure. Okay. The first question that we have done, I think there is some data mistake because the answer is coming to be invalid basically there. So there seems to be some data issue here. Yeah, I think some data mistake is there here. So I'll get back to this probably in tomorrow's session. Don't worry. Okay. I'll start tomorrow's session with this question only anyway. Okay. Any other doubts you have, please let me know. Yeah. This is automatically uploaded on YouTube anyway. And I'll upload this, PDF also. I'll upload this PDF also. Okay. Any other doubts you have? Please let me know. Okay, it's 224. Okay, thanks. Okay, I got the thanks, Ajay. I think it's a data mistake only. So the question actually is 224. So if it is 224, here also it is 224. 224. So this would be 2r square. So now you can't cancel out it completely. Okay. So basically this is now this is this is 2r square. So if it is 2r square, now we can do the calculation. Okay. Send this equation to LHS, then what do we get? We get r square, and then 2r minus 6r is basically minus 4r. 4 minus 9 is basically minus 5 is equal to 0. So on the basis of this, we get, okay, so we can write it as r square minus 5r plus r minus 5 is equal to 0. You can take r common, r minus 5, and then you can write the factors here. You can write the factors and then plus 1 if you take r minus 5. Okay. So then what do we get? We get the factors as nothing but r equal to 5 is one answer, or r is equal to minus 1. Okay. Base can never be negative. Obviously, base can never be negative, and hence yeah. So since base can never be negative, so what I can say is nothing but this can never be a correct answer. Okay, because the radix value uh, can never be negative. Okay, so due to this, we can rule out minus 1. So the only possibility is nothing but 5. The answer is nothing but 5. I'm sorry, there is a data mistake here. As such, the conceptual part remains same. No change in terms of concept, but the only thing is, yeah, instead of 124, it should be 224. Okay. Thanks. Ajay. Thank you. Thank you very much. So magnitude part. So magnitude part, simply remember it like this. That, yeah. If it is sign magnitude format, one step. If it is one's complement format, 2 steps. If it is two's complement format, it is 3 steps. What is the one step? Magnitude bits is equal to simply true format. So how do you get this true format? By converting your binary number into, decimal number into binary format by using the repeated division process. So since I remember all these numbers, I've written it directly. But if it is 11, okay, 11 to the base 10 for you, okay, divide that 11 to the base 10 with 2. Repeated division by 2. 11 by 2 is what? 5. Remainder is 1. 5 into 2, 10 plus 1, 11. Again, 5 by 2. What is 5 by 2? It is nothing but 2. Quotient is 2. Remainder is 1. 2 into 2 plus 1 is basically 5. What is 2 by 2? 2 by 2 is equal to 2 ones are 2. Remainder is nothing but 0. So now you have your binary format. Okay. So that number 11 to the base 10. So we call it as nothing but true binary format. What is the true binary format right now? 1011 base 2. Okay. So this is the first step. So since the number is given in terms of 2's complement format, okay, so the result has to be obtained in terms of 2's complement format, 3 steps. What are the 3 steps? This is a step 1. Convert the magnitude 11 into true binary format 1011 and then complement it. Second step. Okay. 1011 complementation means what? Replace ones with zeros, zeros with ones. So 1 is replaced with 0, 0 replaced with 1, 1 replaced with 0, 1 replaced with 0. Okay, second step. Then add a 1. That will give you the third step here. Okay, so that's it. Now you have got these as nothing but magnitude bits. These are the magnitude bits of basically 11, the number 11, okay, decimal number 11. In what format? In 2's complement format. In 2's complement format. Sir, then what are the magnitude bits in ones complement format? It would be 0, 1, 0, 0. Sir, what are the magnitude bits for the 11, number 11 in terms of sign magnitude format? It is nothing but 1, 0, 1, 1. So we stop here if the representation is sign magnitude format. We stop here if the number is given in terms of ones complement format. We go here if the given number is in terms of twos complement format. Okay? Yeah. Prasad, regarding the questions, I won't say questions, I would say marks. The marks are different from subject to subject. Okay, so if you take electrical paper, 3 to 4 marks only. In EC paper, 10 marks, sometimes 12 marks also. Okay, usually 9 to 12 marks, average of 10 marks. Instrumentation paper, 7 to 9 marks, on an average 8 marks. Okay, computer science paper, almost 10 marks. Okay, so this is the weightage for digital electronics in various exams. Only in electrical paper, it is 3 to 4 marks. Other papers, if you see, probably let's assume EC paper, instrumentation paper, or computer science paper. In all these three papers, on an average, you're having nearly, I would say, 9 to 10 marks easily. Okay. And usually students write in more than one paper, right? So definitely you can't neglect this particular subject because this is a easy subject as compared to others. Okay. Yeah. So I believe there are no more doubts. So with this, we'll call it a day. We'll meet again tomorrow. In tomorrow's session, we will be doing a K-map minimization topic. Okay. Thank you. Thank you for joining this session. We'll again meet tomorrow. Yeah.